So today, so just as of this thing, right? So we have covered till now triangles and polygons, and we, did around 25 questions from those topics. Pretty good questions, really, and like including previous year CAT as well. So yeah, so now continuing on that trend, we'll today start with another major chunk of geometry, which is circles. And the framework for a session would be the same. So we'll cover the concepts that are required from an examination standpoint. That will be like both the some of the basic concepts and also some of the exam friendly shortcuts and tips. And then we'll, as usual, move to the questions right after that, right? So again, the major focus of the session would be on questions, because again, the more variety of questions that you can cover, the easier it is for you in the exam to sort of hit on the concept for the question. Cool. So with that in mind, let's just start with circles. So first thing, right, like at the very basic of it, the equation of the circle you should definitely know, like what represents a circle in the first place. So the equation is x square plus y square plus, no worries, so x square plus y square plus 2gx plus 2fy plus c equal to 0. This is the equation of a circle. Now there are 3 to 4 important points around it. So let's cover them one by one. First is the center of the circle will be minus g, comma minus f. Basically you take the half of the x coefficient and add a negative to it. And similarly take the half of the y coefficient and add a negative to it. So minus g, comma minus f. The radius is root over g square plus f square minus c. So basically again you take the half, square it, take the half, square it, subtract c. Right, so center and radius are the two of the basic, parameters that you can directly like derive from this equation. The important thing, however, is to note that the coefficient of x square and y square should always be 1 for you to apply any of the formulas around equations of circles. So for example, if they give you a question of like 3x square plus 3y square plus something and all, then you have to divide the equation by 3 first, and then and only then you can apply this formula. So just have a check on the, like, if something like this comes, that the coefficients are unity or coefficients are 1 and coefficients are equal. If they are not equal, then it won't be a circle at all. So like for example, if there is 3x square and 2y square, it won't be a circle at all. So this is sort of the first and the basic application of the equation of circles, to find the center and the radius. Of course, there is a simpler form of this that you would have seen, like x minus a whole square plus y minus b whole square equal to r square. This is sort of the simplistic version of the same. Here the center becomes a comma b, radius r is anyways given, so radius is r on the RHS, right? So this is the simplistic form of the equation which everybody would know, and this is sort of the long form of the equation. So this is the first application. The second application of this equation is, so if you're given the equation of a circle like this, and suppose like there is a circle and there is a point P outside, is a comma b, for example, and there's a tangent drawn from this external point P. Obviously, we know that from every external point there can be only two tangents drawn to a circle. So one would be this and the other would be this. But yeah, if there's a, and both would be equal in length. If there's a tangent drawn from an external point to this circle, let's call this circle, his equation is S. So basically the length of this tangent, L basically would be root over S, if you put the value of AB in the equation of the circle. So for example, if this point is 3, 4, so in place of x and y, I'll place 3 and 4 and I'll get the length of the tangent. I'll like take the square root at the end of it and I'll get the length of the tangent. Right, so for example, if they give you an equation of a circle as x square plus y square plus 4x plus 6y or whatever, just place 3, 4 in x and y, take the square root, and I'll get the length of the tangent here. And again, since both tangents are equal, so they'll be the same length. So this is the second application. Now, the third application for the equation of the circle is, and to understand a third application, it is good to sort of see what we do in lines. So for example, if you have two lines having like this having its own equation, this having its own equation, and they meet at a point. So to find this point, you solve the two lines, right? Like you equate the two lines. So somebody has a question? Okay. You equate the two lines, right? So for circles, what happens is if you have an equation here, like for two circles, basically S1 and S2. So for example, S1 is x1 square plus y1 square plus 2gx1 plus 2y1 plus c1. S2 would be x2 square, y2 square, etc. So there are two circles basically. Then the common chord that is there, for example, in this case AB, the common chord which is there will basically be like created, and the equation of this common chord will be S1 equal to S2 or S1 minus S2 equal to 0. Okay, so, and this is sort of very intuitive as well, because as we see that in lines we try to solve the equation of the lines to get the meeting point here. Since they meet at 2 points, so the equation of the common chord will be this. Similarly, if the equation of circle, like if the circles was this, then this equation would have given you the common tangent here. But typically this doesn't, like, then you're not supposed to know as such, but for the common chord it's helpful to know that the equation of the chord here. And also it's also intuitive, because if you see that, so the first step is always to reduce the equation into such form that the coefficient is 1. That is always the first step, so remember that. And similarly you'll do for S1 and S2. So when you subtract those equations or equate those equations, then the square terms will get cancelled, right, and you will be left with a linear expression, which is the expression of the common chord. Okay, so these three things are what you can find directly from the equation of the circle. The fourth, and something that the questions have been asked before as well, is basically, yeah, the fourth application would be that if you are given an equation of two circles, they tend to ask that what is the number of common tangents to the two circles, right? So how many common tangents can be drawn? So there are four scenarios possible, right? Like, you can have basically some like multiple scenarios of common tangent possible. For example, if the two circles are such that one is completely inside, then there is no common tangent, right? So it is zero common tangent, or zero common tangent, or we'll write the CT here on zero common tangent here. If you have a scenario like, for example, there is a bigger circle and there is a smaller circle, but touching the periphery of this, so there will be one common tangent, right? This one, there will be one common tangent, so this is one CT. Right, you can have a scenario where there are two common tangents which are basically like, so if you see the smaller circle is moving to the right and right, so it was completely inside, then it touched the border, now it's just outside, so that they have a common sort of a wall here, and this is called, in geometry term, this is called touching externally. So whenever you see in a problem the term called touching externally, it means that it is this sort of a setup in circles. So here there are actually here there are three common tangents, this and this. We'll cover the two cases as well. Here there are three CTs, and you have a case where there will be four CTs here, like two tangents this way, then two tangents this way. And we'll cover each of these cases like in the remaining part of theory, but to just basically reiterate that there are multiple cases of common tangents that are possible, right? Okay, yeah, and the only other, the two common tangent case was this one. Like, one is sort of what we had for the common chord setup, right? Here there will be only two common tangents, which is this and this. If you touch this, so this and this basically. So two common tangents here. These. Guys, can we please be on time next time on? It's just very, very distracting. Okay, so let's just dive into each of them. So for example, if you have this type of a setup, right, where there is no common tangent. So if you have a center here, like for the smaller circle, somewhere center here for the bigger circle. So obviously here, like, the distance between the centers, if you have, for example, the center of the smaller circle at C1, center of the bigger circle at C2, and the distance between the centers is D. So this is the scenario when D is less than R1 minus R2. D is less than the difference of radius. Okay, and there will be zero common tangents. And please make a note of these, so that, because these will be what we use to like find out the number of common tangent. So this should be actually mod because distances are never negative. But yeah, d like the intercenter distance, which is c1 c2, should be less than the difference of the radii, the absolute value of the difference of the radii. The next one where there is one common tangent is this. So here you can clearly see that if this is the center, this is the center, so this distance, this particular distance would be the bigger radius minus the smaller radius. It is clear from the figure itself. The bigger radius minus smaller radius. So here d will be c1 minus c2 or r1 minus r2. So whenever you get the intercenter distance as r1 minus r2 exactly, that means that it is one common tangent. Okay, for two common tangents similarly, like this particular scenario where you have two common tangents, here it will be in the middle of it. So r1 minus r2 is less than d, but d is less than r1 plus r2. So all of these, like a good way to remember is that the range is always from r1 minus r2 to r1 plus r2. So you have sort of those five cases that less than r1 minus r2, exactly equal to r1 minus r2, then between them, then exactly equal to this, and then more than this. So it's just a, yeah, so basically like this is r1 minus r2, this is r1 plus r2 on the number line sort of. So one case is for here, another case is for exactly here, third case is for here, fourth case is for exactly here, fifth case is for beyond. So that is a cleaner way to remember it. And this is zero common tangent, this is one common tangent, 2, 3, 4, so on and so forth. Right. So this is there. Now for three common tangents, which is the first radius, this is the second radius, so the distance would be the sum of those two, r1 plus r2, as is evident from the figure as well. This will be three common tangents. This is 2ct, this is 3ct. And finally, the two distinct circles, so this will be four common tangents. So here the d will be greater than r1 plus r2, which is again evident from the figure because this is r1, this is r2, and the intercenter distance is much more because of this gap. So this will be four common tangents. So the way to do it is like they'll give you two equations of circles. You can find out the first center, you can find out second center. Using distance formula, you can find out the c1, c2, which gives you the small d we have been using here. Using the distance formula straight, you know the first radius, you know the second radius, you calculate r1 minus r2, r1 plus r2, and then see where d lies. That will determine that how many common tangents, like how the circles are positioned and how many common tangents can be drawn. We'll do a question on this as well with actual values. But yeah, this is the method, right? And it's a like you're not supposed to know anything beyond this for this particular topic, right? Just find out d, just find out r, and you're good to go. And equations we've already covered, like how to find out both of them using these cases. So these are the four basic applications of the circle equations. That too, if you ask like what are the most frequent ones, the first one is a definite must know, and the fourth one is a definite must know. And sort of these are interrelated, right? Because even there you have to find these parameters. But yeah, some of the earlier disclaimers sort of are also very helpful to remember. For example, like ensuring that the coefficients are 1 and so on and so forth. Common chord is good. Common tangent or like common chord is good to know for like just from a awareness standpoint, that if it comes, it is helpful. Length of tangent has been of use at a couple of occasions. Right, but this is probably the simplest of all. You don't need to even calculate anything, just place the values there and you're good to go. Right, and here just the equations have to be subtracted. So that is all with respect to equations of circles. You will not be asked anything beyond that. Cool. So now coming to the next topic, right? The next topic in circles is a very important one called angle properties. Right, and these actually, like there have been questions in the past where like two angles are given, one angle is asked, or two angles are asked, etc., and they revolve around these properties only. And so they're just like two or three properties that you would need to know, three or four properties, and you're good to go on all of those questions. So nothing too fancy here. So the first one is obviously, as you would be very aware of, that the angle at center is double the angle at the on the circumference. So if this is theta, this is twice of theta if they are subtended by the same chord. So if the same chord subtends an angle theta at the periphery, it will subtend 2 theta at this. Obviously, if it subtends at the other side, for example, if this is the same chord and we're looking at this angle, so this chord subtends like infinite angles, right? It can subtend here, 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 anywhere. So if it subtends here, so 2 theta, so this is theta. So basically, then we'll say that this angle is 2 theta, right? So like it should be on the same side essentially of like when you mark the angles. That is probably a good way to remember. Theta and 2 theta are sort of like the corresponding angles of sorts, and here theta and 2 theta, the reflexes of the angles basically. Okay, so this is there. Then the second property is angles in the same segment are equal. So like as we just mentioned that the angles, like one chord can form infinite angles. So here, 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 anywhere, and all of these angles. So like this probably is not the right figure. Let's say this, this. If it subtends one angle here, one angle here, one angle here, all these three will be of the same value, theta, 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 same segment. And how to figure out that whether angles can be equated? Just see the end points of those angles. If it's the same chord that they are covering, then they'll be equal. Okay, so angles in same segment. Then a similar property to this is that there are two chords of same length, they'll subtend same angle at the center, and hence same angle at the periphery as well, because obviously that will be half of what is subtended at the center. So if there are two chords that are equal, for example, uh, this one and this one, right? So they'll subtend an equal angle at the center, is this and this, which is now that you see the figure, it's all is more intuitive as well, because these are sort of vertically opposite. But yeah, as a property also, it's just good to remember. And the converse is also true, that if two chords subtend equal at the center, the chord must be equal. So it works like both ways. Okay. Uh, Third is around angles. So third is now these basically are sort of properties that are with respect to essentially chords and angles, right? Here in like, and all of these are internal angles, if you see here. The third most important property, and this is extremely useful because this is exclusive to circles in a way, is called the alternate segment property, which says that if there is a chord here and there's a tangent here, for example, at this point, then the angle that the chord makes with the tangent, which is this theta, would be equal to the angle that the same chord, it should be again the same chord, makes in the opposite segment. So by opposite segment, what do we mean? That so this chord, every chord divides the circle into two segments, right? For example, if you do this chord, this would be the minor segment, this is the major segment. So if it makes an angle of theta here and this angle lies in a minor segment, so the angle in the major segment would also be theta. This is that's why the name is called alternate segment, because the segment in which the angle is formed, the segment alternate to that, will have an equal angle. And again, the chord has to be the same as mentioned, right? So theta will be theta, and very, very important property here. This usually sort of in an exam scenario, like it helps to prove triangles similar, or if the question directly asks for some of the angles, it helps to derive those as well. So yeah, pretty useful from that lens. Okay, so basically half and double property is done, equal chords, equal angles subtended is done, and like equal angles mean equal chords uh, is also there as the reverse of this. Then the alternate segment is done. So these are the three properties that basically deal with the angles that are internal to the system, internal to the circle, right? Now, if we were to sort of look at the properties for external as well, right, which is, for example, you have this and you have, let's say, this is called a chord, and if it extends like outside, right, so here, so something like this, it's called a secant. So chords sort of ends in a circle. That's like just a terminology, but yeah, still this is a chord and this entire thing is a secant, right? So now if there are two seconds that intersect at angle theta, right? And we should just give it some names, A, B, C, D. So theta will be equal to, since they are meeting outside, theta will be equal to the bigger arc minus the smaller arc. And let me just clarify what this shape means. This shape means the size of the arc. What does that mean? It means the angle subtended by this arc at the center. So for example, if this is the center O, so you just have to see that, okay, where the seconds are meeting, what are the two arcs getting formed? If you see that these two seconds, the big arc is AB, the small arc is CD. You just have to see that. So it's basically half of big arc minus small arc. And when I say the big arc, it's not the length, but basically the angle at the center. So if this big arc subtends an angle of X here at the center, and this smaller arc that is getting formed subtends an angle Y at the center, so theta will be equal to half of X minus Y in this case. Okay, so like in any figure, you take, like, for example, this and this meet at theta, so the bigger will be this one, the smaller will be this one. Fairly direct. Another related formula to this is, what if these meet inside the circle, right? For example, if these meet inside the circle, it's like something like this, right? So what is the angle getting formed? It's like, what is theta here? So these two are like basic chords only, right? So what is the angle getting formed? Here the same formula works, just the minus changes into plus. So basically, what are the two arcs getting formed here? These two are the chords in question. The big arc is this one, the smaller arc is this one. Like it's direct to derive like visually as well, right? So like here, so theta would be equal to whatever this arc subtends at the center minus whatever this arc subtends at the center, and taking the half and sort of just changing the minus to a plus. So if we were to give it some names, basically, so it will be X plus Y if AB subtends an angle of X here. Like this is, like if this is the center, for example, it subtends an angle of X here, and CD subtends an angle of Y here. So the angle at the center, sorry, the angle at the intersection point would be half of X plus Y. These are angles, again, just to remind, X and Y are angles subtended by those arcs at the center. By arcs at the center. In geometry terms, angle subtended by the arc at the center is also called the size of the arc. But yeah, it means the same thing. And again, how to, I mean, it's pretty like intuitive, but how to find the sort of like, what do we mean by when an arc subtends an angle at the center? So for example, if this is the arc, what you need to do is like this angle, right? If this is the center, or the same thing would be that, you know, if the chord subtends an angle theta at the center. So arc AB or chord AB will subtend the same angle at the center, right? So yeah, just from an understanding standpoint. Correct. So if this is, we say the size of the arc is theta, which means angle subtended by the arc AB is theta, which is the same as saying as the chord AB subtends angle of theta at the center, or vice versa. If they tell you that AB subtends an angle theta as a chord, then it means that the arc will subtend the same angle at the center. So if this angle subtended was X and the smaller arc that was getting formed, let's say this, if this was Y, then the intersection angle wherever these chords intersect would have been half of X plus Y. Okay, so those are basically the important angle related properties here, right? And yeah, any questions at this point? And in this case, like, all of these are important, so like, yeah, I should remember all of these.
Hello.
Yeah, please go ahead.
Yeah, so in the second figure, where the chords are intersecting inside the circle,
Yeah.
So angle is, so which angle should we take? It's CO, that's theta, or that is 180 minus theta. So that's the
Okay.
confusion
Okay.
I'm
Yeah.
facing.
Yeah. Fine. So yes, you're asking whether it should be this one or this one, correct?
Yeah.
Yeah, exactly. So it would be the acute angle basically. Like it would be this angle. Like this and this would be anyway equal, but yeah, like this angle will not be taken. Like whichever is the acute angle would be generally taken.
Okay.
Right.
Okay.
And even in general, like you try to, like, if you like sort of the angle is taken with the positive direction of the X. But okay, like no need to get into that. But Yeah, this should be
Mhm.
theta, which is the acute angle.
Okay, okay, got it. Thank you.
Okay, no worries. And similarly, like again, the same thing would be happening if you have, instead of seconds, like tangents intersecting, right? So it's the same principle. If let's say this was these two were the tangents, and they asked you this angle, again the exact same thing basically, right? So the one arc will be formed by, like, let me just extend this time here. So the bigger arc will be this one, the smaller arc will be this one, but again the same formula. Obviously, tangents cannot meet inside, so this scenario will not be possible. But yeah, this scenario will still have half of x minus y. X is the angle subtended by this, the sort of the bigger arc at the center. Y will be the angle subtended by this one at the center. So it's just a boundary case of the second theorem. Okay, so with that done, we should be able to move ahead. Now we'll come to two terms that you would be familiar with, but just to revise, which is the sectors and segments. How to find the areas, etc. Because typically in questions of circles, which involve, like, you would have seen questions like find the area shaded, or what is the area lying between these two circles, or circle and a triangle, etc. So wherever circles are involved, typically the area questions do involve some amount of sector or segment based working. So it's helpful to cover that. So in any circle, if you draw a chord, the sector basically is, if this is the center, this is the sector. Like like when you also join the chord to the center, and this entire area is a sector, right? And this angle is, let's say, theta. So if the chord subtends an angle theta, this entire area is a sector. So the area of sector is pi r square. R is of course the radius, pi r square into theta by 360. Why? Because the full circle, if it was 360 degrees, you would have the area pi r square. That is the entire circle area, right? So if 360 gives pi r square, then theta would give how much? So pi r square theta by 360. A unitary method, that's it, nothing else. So if you're given that a chord subtends an angle of 60 degrees at the center of the circle, find the area of the sector created. And again, this is the smaller sector. The other sector would be like this entire area, like basically this entire area, right? So find the area of the minor sector created. So the minor sector would be this one. If they ask you the major sector created, then the major sector would be the total area of the circle minus this one. Right. So pretty fundamental. Right now, this is the sector. Now, if you see carefully, the sector is made up of two parts, really, right? So this was the chord, and this, we said, this entire area was the sector. Right. The sector is made up of two parts. One is this triangle, and one is this area. This area is called a segment. And the reason I'm trying to explain it that way is because segment area will always be calculated as sector minus triangle area. Right. Now, what happens if this is radius, this is radius, this is theta? We already know the sector area is pi r square theta over 360. And this triangle area, we know by the sine for base formula for triangle, it will be half r square sine theta. So this basically, if you take r square common, so you'll, again, no need to memorize this at all. All you need to definitely know is segment is sector minus triangle. So whenever you need to find the area of segment, that is the working to be followed. Okay. So yeah, so this is a segment, and again, this is again the minor segment as we have defined the sectors. The major segment would be the remaining part of the circle, like whatever lies above this chord, essentially. Whatever lies below was the minor segment. So this is the sector and the segment. Again, useful for area-based questions, definitely. So good to know. Okay, now we come to the third and very important aspect of circles, which are properties around tangents and seconds. So as we just covered, right, like the chord being extended out till outside, like this and this, etc. These are called seconds here. So we have A, B, C, D. So the first important law is the second theorem, or the second proportions theorem, which basically says that PC into PA will be equal to PD into PB, which is basically small into full will be equal to small into full. And you can like draw infinite from it, right? Like for example, if there was another one like created like this, let's say this was M, this was N, this was Q, this was R. So this will also be equal to PM into PN, also be equal to PQ into PR. So all these things will always be equal. So if the second is drawn from the same point, the product of the proportions will be equal. By product of the proportions, you mean the partial, like the part that lies outside, into the total. So in this case, for example, if we took PC into PA, so PC was the part that lied outside and PA was the full part, and similarly for the others. So pretty important here. Right. The second is a border situation of this, wherein you have a tangent and secant. Right. So for example, this is a tangent here, and from the same point, again, all of these properties are valid if they are from the same point. And here something like this, or here, right? So PM, PN, PQ. So the second is the tangent secant theorem. And these really are very important because typically these are questions where it will be almost directly visible that these are getting used, right? So should be able to solve them. Pn square will be equal to, if you have these points, at PR into Pn will be equal to PS into PQ. Again, you draw like n number of things, all of them will be equal. Once again, external part into the whole, external part like partial into the whole, and will be equal to the Pn square. So this is a tangent secant theorem, right? And again, you don't even need to like be specific about Pn. Even Pn would have the same property because tangents from an external point are equal. So Pm equal to Pn in above. If you draw, and from any external point to a circle, there can only be two tangents. For example, if you have a circle and any external point, there can only be two tangents to the circle from this point, and those two tangents will be equal. So that is what is written here. That Pn will be equal to Pn, and these are, yes, these are lengths. Yeah, that was my bad. So it relates to this figure actually. So Pm equal to Pn. That's done. And this actually, this result comes of use at many places, as we'll see when we start with the questions. But like for example, if you have a triangle, right, and a circle here, right, immediately you should realize that these will be equal. This will be equal to this. This will be equal to this. This will be equal to this. Right. So like even if not given in the figure, and if you feel that it's helpful, it's just like as soon as you read the question, these are sort of good mental notes to make, that okay, I know that this can be done. Okay. Similarly, if you have even a circle outside of the triangle, let's say this, let me just start on a new page. Like for example, if you have a scenario like this is a triangle. This is again sort of a common setup that comes, which is this. Right here, the circle is outside the triangle, but still you can apply. For example, if this is the P and Q, the points of tangency, you would know that, like basically, like there's a question actually on this concept that was asked. That was, they gave the length of AP as, let's say, 10 or whatever. It doesn't matter. AQ as like 15, and then they asked you to find the perimeter, and they gave BC, and they gave one of the sides or something, and they asked you to find the perimeter of ABC. Right. So basically, if like this length is equal to this length is equal to this length, that was all the question was about. So basically, this plus this will be equal to the perimeter of this. Let me just write it down, right? So if, for example, if this is point M, so what is the perimeter? And you're given these two, you're asked to find the perimeter of ABC. What is the perimeter of ABC? AB plus BC plus AC, which is AB plus BC is nothing but BM plus MC plus AC here. Okay, now we know that BM is nothing but BP, MC is nothing but CQ, plus AC, right? AB plus BP is nothing but AP, CQ plus AC is nothing but AQ. So the perimeter of the triangle is nothing but 10 plus 15, 25. That's it. Right. So again, very basic, but yeah, just sort of shows that how it's an important thing to just sort of make a mental note whenever you see that you can utilize this property of tangents from the same point being equal. So so basically in this case, yeah,
Sir, but AP and AQ are tangents both from the point A, then how is AP 10 and AQ 15?
yeah, these should be equal. Yeah, these should be equal. Yeah. So yeah, let's take them as 15 and 15. Good catch there. But yeah, the principle holds that basically you need to sort of have like just took random numbers from here. Didn't notice that, but yeah, essentially that is the funda that you need to like basically just see, and there are no sides given of this triangle if you notice, right? But you have to find the perimeter, so there is no other way just to have this sort of uh, like equivalence of tangents from the same point being equal, and to show that these lengths of the tangents will be equal to the perimeter of this triangle. Okay. While we are at this figure, it's an important figure, and I just recalled something, so I'll just share that with you here. It's an important figure because it's a unique figure. It's one of those figures where if you see that, you'll recognize it immediately, right? Like a triangle drawn and then a circle drawn outside of it and not inside of it. Please remember, this circle is called the X circle of the triangle. Like the inside circle was called the in circle. This external circle is called the X circle of the triangle. Okay. So, and we had like a couple of formulas for in center, like around area and stuff and all of that, right? But we never discussed this X circle. This is the only case where sort of the X circle comes valid, because this is the definition of an X circle, and the radius of the X circle, like if it is made, and again we have the general notation of A, B, and C. If it is made here, like on side small a, then the radius of the X circle will be area of the triangle upon S minus A, where S is semi-perimeter of the triangle, which is A plus B plus C by 2. Similarly, if it was made on, like if you make a similar circle on B, right? If you sort of make a similar circle on B such that it is tangent to that side here, something of this sort, then this radius, so this will be RA, if you can say, if RB on the small, and again B refers to the small letter side, not the vertex. So RB will be area upon S minus B. And yeah, it's a direct question actually that's been asked, so that's why uh, it may be just good to know that area upon S minus B. Similarly, if you have a X circle on side C, so it will be area upon S minus. Cool, and this is only valid for this sort of a figure wherein you have a circle made outside of a triangle. Any questions there? It's easy to derive, but we'll get to the derivation at a later point.
Sir,
But yeah,
can you explain this last property once again?
sure thing, absolutely. So this is a triangle, right? And we have discussed the in-center before. We've discussed its various properties as well, right? Like area and other properties and stuff. This is the X circle. It is like the circle made outside the triangle but tangent to one of the sides of the triangle. For example, this circle is in contact with the side A, which is tangent to the side A basically. Similarly, you could have drawn another circle which is tangent to the side B here, something like this. Similarly, you could have drawn another circle which is tangent to the side C, something like this. Right. And so all you have to see is that where the circle is getting built, like if it's on side BC or if it's on side small a, then the radius of that circle, and again that the sort of the circle spans between B and C here, like if you see, right? So this circle is like the boundary is AC. This circle, the boundary is AB, right? So in that case, the radius of this circle is called the X circle. The radius of the circle will be area of the triangle. This is the area of the triangle. And upon S minus A, S is again the semi-perimeter, which is A plus B plus C by 2. The normal semi-perimeter that we know. and A is the side length here. So let me just do a basic question on this, probably that will immediately clarify stuff. So if we have a triangle of 11, 12, 13, right, and you have this, you can find out the area of this triangle by Heron's formula. S is nothing but 11 plus 12 plus 13 by 2, which will obviously be the middle value 12 in this case. And okay, no, that is by 3. So this is 23, 36, this will be 18. So S is 18, and you know the area. So the radius of this particular circle, which is, let's say, RA, small a because it's built on the side, this one. So the radius of this circle would be nothing but the area, whatever you find out here, upon S minus 18 minus whatever the side length is. So in this case, it is 13. Like the side on which the circle is built, basically. That side you have to see where the circle is built. So it will be A by side. This radius is called the X radius. Obviously, it will be different depending on which side the circle is getting built, because if you see the formula itself, right, like area and small s will remain the same, whether it's this circle, whether it's this circle, whether it's this circle. Area of the triangle will be the same. Semi-perimeter of the triangle will stay the same. So this length will change, which means the X radius will keep changing depending on what side you are building the circle on. So that is the only thing that you have to see, that what side is the circle getting built on. So the moment you see this figure, it should immediately strike you that, you know, instead of going the long route, you can use the X radius formula. Which is, once again, just to write it in perspective, S minus A, and once again these two parameters are triangle parameters, area and semi-perimeter. This is the side of the triangle itself, but which can change depending on where you build the circle. And you'll see this diagram in every study material, but they derive they derive the radius by like dividing it into triangles. They actually derive this formula by dividing the figure into like 3 or 4 triangles and then calculating. They like join here and then divide it into 2 triangles and then use that. But this is the result that is useful to know, of area upon semi-perimeter minus the side. Fine. So this was just a small thing because we were discussing like a figure similar to this on the perimeter question. So that is why I just decided to mention it here. So basically what we now know around like the length of tangents and seconds is that tangents from like same point are equal in length. The second theorem we just covered that, okay, like the product of the proportions will be the same if the tangents seconds are drawn from the same point, or if the seconds meet outside at a point. You can frame it either way. Like basically mean the same thing, right? And then the tangent second theorem as well. If the same point has a tangent, if the and the same point is being used to make seconds, then the tangent square will be equal to the product of the second proportion. The last one in that sort of the family of theorems on like tangent, second, etc. is not exactly a tangent on a second, but a chord, which is like a bounded second or whatever. So A, B, C, D are 2 chords, and again, this is just a general point of intersection, not necessarily the center, right? So for example, if they intersect at M, then the opposite product will be equal. So AM into MB will be equal to MD into CM. Very important from a question perspective. And again, all of these properties are very important because, you know, as mentioned, right? So just by looking at the figure in the question, or when you draw the figure from the, you know, question wording, you'll immediately identify that, okay, seconds are intersecting, tangents are, you know, sort of being created, or chords are intersecting. So these formulas might be of use to me. So that is why these like at times come to direct application there. So basically AM into MB is MD into CM. So like the opposite proportions, their product is equal. Right, and similarly, if you draw like another chord from the same, the meeting points will be the same, of course, but if you draw like PQ here, so then this would also be equal to PM into MQ, and so on and so forth. Okay. So these were the major formulas around the lengths of tangent, seconds, etc. Right. Some properties do remain same, like, or not properties I should say, but let's say some like solving techniques remain the same between what we have discussed for triangles and polygons and what we'll discuss for circles. So for example, if you need to find the area between some things, then again you need to break down the figure into figures that you know, and then like add and subtract based on the combination that is there, right? For example, let's say there are three circles here, each of radius, it really doesn't matter, but let's say radius 2 each, or it could be different also, it really doesn't matter, right? So but let's take, if it's all of radius 2 and you need to find this area, how to find this area? There is no direct formula for this area, right? Obviously it's an irregular shape. So once again we need to break it down into figures that we, or like formulas that we know. So in these cases you will join the center here, centers here. Obviously this will be 2, this will be 2, this will be 2, 2, 2, 2. So this is an equilateral triangle of size 4. Right? And equilateral triangle means that these angles will be 60 each. So how can I find this area now? I'll just calculate the area of the triangle, subtract the 3 sectors that are getting made, and those 3 will also be equal, right? Because it's the same angle and same length as well. So those 3 will be equal, and I'll get this area. Always remember that in questions around circles where you have to find areas, right? It is like 99% of the times there will be some triangle getting made, and we'll cover some questions also that illustrates this, but there will be some triangle getting made wherein you'll have to apply things like this. Like in this case, there was an equilateral setup. In some cases, there might be a right triangle. In a lot of cases, there are right triangles getting made, and you have to apply like Pythagoras and stuff. But generally, like for triangles, for circles and areas based questions, there'll be some like triangles and etc. getting formed, or like some sectors readily available in the question, because like, even segment is a like sector minus triangle only, right? So here, like in case like this is a sector, there are 3 sectors. The equilateral triangle of side 4 will have the area of root 3 by 4 4 square, and minus the area of 3 sectors. The area of each sector would be what? Pi into r square. R is 2. Again, r for the sector. So pi into 2 square into theta by 360. What is theta here? Because the equilateral triangle, so 60. So 60 by 360. This is the area of one sector. You need 3 sectors here, so 3 into this. This will be your answer for this area. Again, fundamental stuff, but yeah, it just helps to sort of see visually that, you know, how to sort of estimate the areas of even irregular shapes like the one here.